In the previous video, we have seen how to filter the element constraint with variables, but not for domain consistency, for a kind of hybrid consistency. Now what we will see is how to do it for the domain consistency. That's the strongest possible consistency that you can dream about to remove all the infeasible values for element constraint. So let's consider first a small example there. As previously, we have the domains of the target variable z, which is represented here. The domain of the variable y, the index variable, is represented there. And you see also vertically, okay, increasingly the domains of each of the variables in the array T. So what are the values that we can remove there? First, we will do the filtering from T and Z in the direction of Y. So we will first be interested to filter the index variables there. As you can see, the filtering that we use is this one. We will check for every index, so the indices are there. If for a given index, we see that there is no intersection between the domain of the T variable at that corresponding index and the domain of Z, then we can remove the corresponding index from the domain of the variable Y. Okay, so which one can we remove? Well, you see that for the first one, there is a common intersection there, so we cannot remove this value 0. For the second one, for T1, we can remove it. Okay, we have these only two values, but they are not part of the domain of Z, so we can remove the value 1. And that's the same for the value 2. You see that these two values are not part of the domain of Z, so the index 2 can be removed from the domain of Y. This one, we cannot remove it because there is at least one possible common value there, which is the value 6. Okay, that's the first rule. But as you can observe, this can be quite slow because we need to efficiently compute the intersection between the T variable domain and the domain of the variable Z. So how can we do to make that a little bit more efficient? What we will use as a technique to speed up the computation there of the intersection and then detect that it's possibly empty is that we will use support caching. Okay, in case it's not empty, so in case we cannot remove this value I, then we should remember the common value that is part of the two domains. Okay, we will remember at least one value that is part of the two domains. And we will store that value in support T of I. Okay, so for every index I, we will remember that value from the domain of Ti that is also part of the domain of Z. Okay, and the idea by doing this caching is that hopefully the next time that you will call propagate, this value will still be part of both domains, and so the intersection will still not be empty, and we will not be able to remove it. Okay, and so we will spare a lot of computation if the intersection is not empty, and we can verify that in constant time. But in the case the support is not part of the domain of Z, then we need to look if the intersection is really empty. And so in that case, we have no choice to iterate over at least one of the two domains because they're implemented with sparse sets. And so we might be in the order of the size of the domain of Ti in that case. Okay, but in the case, if the support is still valid, then we can do that in constant time. So that's one way to speed up that filtering rule for the element constraint if you want to achieve domain consistency. That was the step, the first step. Okay, that was the first step. So filtering from T and Z in the direction of Y. Okay, and so in that case, the two values that we'll store in the support caching values are these two values because you see that these are the only one that is common to both domains. So that's the two values that we would store in support of T for the index 0 and the index 3. The second rule that we can apply is filtering in the direction of Z. So we take into account T and Y, and we will consider the filtering of Z. To do this filtering, we need to consider each values one at a time. And if we realize that this value, for instance, the value 7, okay, is not contained in the domain of any index variable, so in any variable in T for which the corresponding index is still valid, then we can remove this value V from the domain of Z. That's the case for the value 7. Look at the value 7. You look horizontally, okay, and you find no value in the domain of T0 or T3. Okay, so therefore we can remove the value 7. That's the same for the value 4. You look horizontally, and you see that, well, here it's quite clear because the value 4 is not part of any of the domains. So we can remove this value 4 from the domain of the variable Z. Again, this might be quite slow to compute because for each of them, you possibly need to iterate over all the array T just to look for one intersection. Okay, and checking if it is part of it, of course, since it's implemented with parsed, you can verify that in constant time. But still, the non-existence check might take something that is linear in the number of variable in T. So how can we speed up that check as well to filter the domain of Z? Is also using this idea of caching the support. And so we will introduce for every value of the domain of the variable Z, for every value in this domain, so for every value V, we will also store a support that will contain the index of one variable of T, so that this value V belongs to the domain of Ti. Okay? Because the next time that you will call propagate, there is a chance that this value is still valid. Okay? It's still valid in that case, and that in that case we can verify it in constant time. So you can again save a lot of computation using this idea of support caching also in that direction. And so in that case you see that the support caching that we would store is this one. Okay, so for the value 6, the intersection is not empty. So I will remember that it was for index 0 that the intersection was not empty. Okay, and this is where I should verify if the support is still present or not. And the last direction of filtering is filtering the domain of the T variables. Okay, so all these domains. And again, in that situation, you can only do it if you realize that the domain size of the variable y is equal of 1. Okay, but if the arity of the domain size, so the domain size of variable 1, y is not 1, then you cannot remove anything because you don't know in which variable you should remove it. And it's quite clear in this example. For instance, look, you see that the value 6 there, okay, is there, but it's also present for T of 0 and T of 3. Okay, and so we don't know yet. Okay, we know that Z will take the value 6, but we don't know yet if it will be from the variable T0 or T3. And so we cannot really decide, and so we cannot print anything here on this domain and on this domain. Okay, so we can only force the equality between the two variables, so the variable Z and one of the variables there, when the domain size of y becomes 1, not before. Interestingly, the value that we'll store in the support arrays are still valid on backtrack. Because look, when you go down in the search tree like this, you will only remove additional values. Okay, so when you go down there and you update the cached values, when you will backtrack, okay, to an ancestor node, then these values that you have in the cache are still valid ones. Okay, they will still be, for instance, a value that corresponds to a non-empty intersection. Okay, so they are still valid on backtrack. Therefore, there is no need to store these cache values in reversible integers or state integers, because you know that when you backtrack, they will still be part of the domains.